to the Journey Shake Hand. It's very important that you write these warm-up questions down in your composition notebook. And you may want to put the answers that you think they are below, way below that, or on the next page, so that you can cover those answers and try them again. That's always good practice and good review. Well, do the best you can, please, and we'll discuss them in a moment. In number 1, once again, we have a table. And you'll notice that the table was not given in the same order as the last table. Therefore, you need to learn the concepts and not memorize the way the table is arranged, because tables change and you need to know the information. Well, here we have selenium. And I look on the periodic chart to see its atomic number, which is the number of protons. And I see that it's number 34. I'm going to write 34 here. The atomic mass is my top number of 80. The atomic number, which is my Z, is also the same as my number of protons. Then my number of neutrons is the difference between the mass minus the atomic number. And when I see the difference here, I see that it's 44 neutrons. And the electrons now, we have stepped it up a little bit here. We have a charged ion. This has a -2 charge, which means that it gained 2 electrons. We originally had 34 in the neutral atom. We gained 2, and therefore we have 36 electrons. In the second case, we have the copper ion. And our top number is our atomic mass, which is 65. And I'm going to go ahead and write that in. Now the atomic number, or the number of protons, is 29. Again, I'm going to write it here on the lower part where it normally should be. And therefore we have 29 as my atomic number. The difference between these two numbers is my number of neutrons, and that would be 36. And the electrons, we have lost 2 electrons, and therefore we have 27 remaining electrons. Antimony here has an atomic number of 51. Therefore, it has 51 protons. My atomic mass is 122. My atomic number is 51, which is the same as the number of protons. My neutrons is the difference between those two numbers, and that would be 71. Now, this is not a charged atom, and therefore I have the same number of electrons as I have protons, and therefore that would be 51. In this case, we are not given the symbol, but I know it has 26 protons, and therefore it has 26 as its atomic number, and that would be iron. My atomic mass is 26 plus the 30, which would be 56. The protons plus neutrons give me my atomic mass. The number of this 30 was the number of neutrons here. It should be here. The atomic number is the same as my number of protons. And the number of electrons, this is not a charged atom, and therefore it must be the same as my number of protons, 26. And we had a little bit of review from yesterday's information. That's how you do number 1, and we'll be right back for number 2. In number 2, we are reviewing the concept that we discussed yesterday on average atomic mass. And the average atomic mass is a combination of all of the isotopes that have been found in nature. And in this case, we have 3 isotopes. And it is given to you respectively, which means that the numbers are given in the order that they are given in the problem. We are given 23.9924 as our first mass of our first isotope, and we're given 78.6%, which we must change to a decimal. Then we multiply it out and get 18.8580. Remember, we take it 4 places after the decimal and cut it off. The second isotope has a mass of 24.9938, and it is 10.1%. And therefore, we change it to a decimal, we multiply the two numbers together, and we get 2.5243. And then the third isotope has a mass of 25.9898, and it is 11.3%. And therefore, we change it to a decimal, and we get a number of 2.9368 for its proportion of the isotope that occurs in nature. Then we add the 3 up because the 3 together give me the whole pie, and I get a mass of 24.3191. And then I round to the tenths place, and the 1 does not round the 3 up. And therefore, our final answer is 24.3 AMU, atomic mass units, is my label or my unit. And we must take it to the tens place for our final answer. And this would be the average atomic mass of magnesium. Now we're going to talk about some notes, and please get out that blank periodic chart. Let's take a few little notes. Well, you need to take out that blank periodic chart so that we can write our notes on it directly. And that's a good study guide because it's going to have a lot of things on it by the time that we're done before the assessment for this very first topic. Well, the blank periodic chart looks very similar to this. And you'll notice on the first energy level, these are my energy levels. And on the first energy level, there are only 2 spots. Only 2 elements, and that would be the hydrogen and the helium. These energy levels that go down, we call those a group. And when we move across, we call it a period. And that keeps us straight because we're going to be talking about many, many things on this blank periodic chart. Well, you'll notice on the first energy level there's only 2 elements. Well, that is because of what we're going to discuss right now. And we had drawn the Bohr model of the atom the very first day of school. And we said that inside the nucleus was the proton that was positive and the neutron. And then orbiting outside were the electrons. Well, we know that this Bohr model is not the way it actually occurs, but for simplification, it works very well for us to introduce it. Now we are at a point where we know that these electrons are orbiting around the nucleus, and where they're found is called an orbital. That is a probability area of where we are likely to find those electrons, and they are in various different areas. Well, the first area and the first type of area of probability that we have is called the s orbital. And you'll have to remember that these are areas of probability where we're likely to find the electron because the electron is constantly moving, so we don't know exactly where it is, but we know we're going to find it somewhere in this spherical area. And because it's in the spherical area and we know that they're three-dimensional, atoms are three-dimensional, it's a sphere. And we have a rule that is called Pauli's exclusion principle. And that tells us that there can only be 2 electrons in any orbital. No matter what kind of orbital they are, we can only have 2 electrons. And therefore, on the first energy level, we have this s orbital with a maximum of 2 electrons. And you'll notice with 1 electron, we have hydrogen because the atomic number is also the number of electrons in the neutral atom. And for helium is atomic number 2, so it has 2 protons and 2 electrons in the neutral atom. On the second energy level, we have what are called p orbitals. And that sublevel has 3 p orbitals, and they look like dumbbells. And because it's three-dimensional, we have one along the y-axis, one along the x-axis, and one along the z-axis. And a textbook would have a much better diagram than what I can do. But for illustration purposes, this is fine. And we can have 2 electrons per orbital. So in the p sublevel, and orbitals and sublevels are terms that we use somewhat interchangeably, the orbital is actually the probability area of finding those electrons, and the sublevels are the s and the p would be considered sublevels. Well, you'll notice in the second energy level of the periodic chart, we have 8 different elements that have those electrons. So we have the second energy level, which has the s orbital, and then it has the p orbitals, or the p sublevel. And because each one can contain 2 electrons, that gives us a maximum of 6 electrons in that p sublevel. And also, because we can only have these 2 electrons, they spin in opposite directions. And what happens is that when we have more than 1 electron that we are filling these p orbitals, we fill 1 electron per orbital, and then we go back and we put the second one. And I show them as arrows spinning in opposite directions. And this is called Hund's rule. And Hund means dog in German. Not that that helps us remember it, but it is called Hund's rule. And I call it the school bus rule because everybody wants their own seat. As we get onto the bus, everybody takes a seat, and then when the bus gets full, we have to double up. So we put 1 electron per orbital and then go back and fill those orbitals. Now, on the third energy level, we pick up what is called the d sublevel, the d orbitals. And the d orbitals are a little bit more complicated, and we really don't need to know the specifics about how those are. But we do need to know that on the third energy level, we have the s orbital, we have the p orbitals, and then we get the d orbitals. Now, you'll notice that the maximum number of electrons that can fit into the d sublevel is 10, and therefore there must be 5 d orbitals. Then on the fourth energy level, we have the s and the p and the d, and then we have the f sublevel. And you'll notice that the maximum number of electrons for the f sublevel is 14, and therefore there are 7 f orbitals. And then the 5th, 6th, and 7th energy level just follow the same pattern as the 4th. So we have the 5th energy level that has the s, the p, ooh, that's a 5, the d, and the f. And then we have the 6th energy level, and the 7th energy level. Now, Pauli's exclusion principle also tells us that electrons will fill the orbitals with the lowest energy first. And when we do what are called complete electron configurations, which is one of the things we're learning today, we have to follow what is called the diagonal rule. It's also called the Aufbau principle. And again, in German, Aufbau means to build up. And it builds up from the lowest energy level up. And I use the diagonal rule to know how they fill because it's the easiest for me. I draw out each one of the energy levels and the orbitals that are in them, and then I put a diagonal line through the first orbital and then the second orbital, and then my diagonal lines will follow in the correct pattern. And what we do is that we look at the periodic chart, and let's try to look at one. Oxygen is atomic number 8. It has 8 protons and 8 electrons in its neutral atom. So I know that we have 8 electrons. Well, I follow the diagonal rule until I get to 8. These are the maximums. But if I only need 1, then I only put 1. And I go 1s2 down and then back up to the tail. 2s2, then down, back up to the tail, and then 2p4. And I have 8 electrons that I need to consider, 2, 4, and 8. And this would be the complete electron configuration for oxygen. Now let's look at sulfur. Well, sulfur has atomic number 16. I go 1s2, back up to the tail, 2s2, back up to the tail, 2p6, down 3s2, back up to the tail, and then 3p4. So it goes 1s2, 2s2, 2p6, and 3s2, and 3p4. And we count to make sure we have the right number. 2, 4, 10, 12, and 16 electrons for sulfur. And that's how we do complete electron configurations. And what we have to be careful of is after we get to 3p6 and we go down, we see that we fill the 4s2 before we fill the 3d10. And it's very important to follow this diagonal rule until we get to the number of electrons that are required. And you'll notice here, this number of electrons is a total of 8, and when we look at the second energy level, we see that we have 8 atoms that fill that second energy level. And notice when I did the oxygen and the sulfur, they have the same ending electron configuration. They end in S2 and P4 if we don't consider the energy levels. Now those are the valence electrons. And I see that everything in this first column will end in S1. And then we will have S2. Then we skip over to this area here. We're going to skip the center and we're going to move here first so that we get some of the basic ideas. Then we have S2P1. Then we have S2P2. Then we have S2P3. S2P4. Oh, I have to change it a little bit here. That happens from time to time. S2P5 and then S2P6. Now you'll notice that above the S2P6 we have helium. And when we look at helium's electron configuration, helium has atomic number 2. And therefore it has 2 protons and 2 electrons in its atom. And when I do a complete electron configuration, it's just 1s2. And I notice that on the first energy level, there's only an s orbital. And therefore, once the helium has those 2 electrons, and we call it a duet, then it has a filled energy level. It is very stable, has very low energy, and it's placed in this column with the rest of these elements that are also very, very low energy because they have a filled energy level. And they fill their energy level with an S2P6 arrangement, whereas helium fills it with an S2 arrangement because helium only has the first energy level. And the rest of them, once they get to the second energy level, there's a possibility of being S2P6. And these here are called the noble gases or inert gases. And they are noble because they have the S2P6 arrangement, except for helium having the S2. And that's very important to keep straight, and that's why they're all in the same column here. And the column would be called the group. Now these outer electrons, those are called the valence electrons. Those are the ones that are available for bonding. They are extremely, extremely important, and it tells us a variety of different things as to how they will behave. Well, we have what are called Lewis dot diagrams. Lewis dot diagrams. or just dot diagrams. And what the dot diagrams are is that we take these valence electrons and we make dots out of them and we place them around the element. For example, if I have hydrogen, well, hydrogen has one dot. And then fluorine over here is going to have 7 dots. We have the S and the P electrons only. Those are the only ones for the dots. And I add them up. 2 plus 5 is 7, and therefore fluorine has 7 dots. And I will make a note here that oftentimes people will put them in a specific order, but I don't really care about that. I just want them around the element as though we're in a box with 4 sides. I don't want them out in a row because then they wouldn't be available for bonding. So we put them in a box and we put the dots around. And I like to put little circles, and later on you'll find out we do some other things with them as well. And that's how we do the dot diagrams. And therefore everything in this first column will have 1 dot. Everything in the second column will have 2 dots. Then we skip over to this area here, and boron will have 3 dots. And then we have carbon, which has 4 dots. And nitrogen has 5 dots. 2 plus 3 is 5. And then we have oxygen, which has 6 dots. S2P4 is 6 dots. And then fluorine, we said, had 7 dots. And helium has 2 dots, but the rest of the noble gases, for example, argon, would have 8 dots. When something has 8 electrons around it, an element, we call it an octet. And that is a very stable, low energy electron configuration to have an octet. And that's what everything wants to be. And a lot of times people don't like it when you say happy atoms, but I like happy atoms, and happy atoms have an S2P6 arrangement, except for helium has a duet with S2. But happy atoms are S2P6, and that's for most of them. And so I call them happy atoms. I don't care. That's just the way it works for me, although we need to be aware that it also means that they have a low energy and a filled energy level. And so we understand that, but we like to say that they're happy because we like to be happy. And so those are the dot diagrams for those elements. Now, another thing that we need to discuss are the oxidation numbers. And we talked before about ions, and that when an element gains an electron, it becomes negative. And when it loses an electron, it becomes positive. Well, when we look at something like sodium, which has atomic number of 11, sodium has atomic number 11, and therefore it has 11 protons and 11 electrons in the neutral atom. It's not charged here. And I write out the complete electron configuration. 1s2, 2s2, 2p6, and 3s1. And indeed, it is on the 3rd energy level, and it is in the s1 column. Now, when sodium loses 1 electron, it would lose this electron here. As it does that, it becomes positive. And notice what's left is an S2P6 arrangement. And that makes it very happy. So it doesn't care about losing that 1 electron. So everything in this first column will have a +1 charge. Now we know that hydrogen is a non-metal, even though it's in this column. It's put there because normally it will also want to lose that 1 electron most often. And however, it could gain 1 electron, but usually it loses 1, so it's placed in this column. Then in the second column, it also will want to lose those electrons. And when we look at magnesium, which is number 12, it is 1s2, 2s2, 2p6, and 3s2. By losing those 2 electrons, we're left with s2p6, and therefore everything in this column will be +2. Now, in general, I'm just giving some basic ideas, and there are differences, as we'll learn later on. But right now, we just need to see the trend. And the trend here, S2P1 will lose 3 electrons. And S2P2 will lose 4 electrons. And again, I reiterate, these are not always, always, always. But for us at this point, this is what we need to understand. You'll notice that nitrogen is S2P3. Now we're getting very close to S2P6, and therefore in this column they will gain 3 electrons to become the S2P6 arrangement. Carbon will not want to do that. That's too many electrons to have to gain 4 electrons. It takes too much energy. Easy to lose them. Easier. It's much easier to just lose them than it is to gain them. It takes some energy to gain those electrons. So at the nitrogen column, this S2P3, they will go ahead and want to gain those 3 electrons. They have great pull for those electrons. Oxygen is S2P4. It wants to be S2P6, and therefore it will have a -2 or -2 oxidation number. S2P5 is only 1 away, so indeed it will want to gain 1 electron and have an oxidation number of -1 or -1. And we said the noble gases, they don't want to do anything. They're just happy the way they are, so they just like, leave me alone. I don't want to gain electrons. I don't want to lose electrons. I just stay where I am, and that would be a 0 oxidation number. And so we've discussed the dot diagrams, we've discussed the ending electron configurations, we've discussed how to do a complete electron configuration, and we're going to need some practice at doing those. I always have to write my diagonal rule. I can't remember that. And we take a little bit of notes every day, and as we move along, they add up. And before you know it, you're going to know a lot of chemistry. And we have all of this on our blank periodic chart, and that's the notes that we had for today. Well, you get to practice them tonight. I know you do well. We'll discuss some more tomorrow, and I can't wait to see you then. Bye.